Right, in this video, we're going to talk about how to use matrices for the simple linear regression model. Let's remember, what is the simple linear regression model? Up until this point, we've been talking about it using this notation with subscript I. So yi equals the intercept plus the slope times x sub I plus epsilon sub I. Okay, and we said that's for I equals 1 to n. Right? So when we're using matrices, the big difference is instead of using this subscript I and writing the equation like this, we're going to use a vector y and a matrix x, and then a vector beta, and then a vector epsilon. Okay, so this is the exact same model, it's just written with vectors and matrices. So what are these guys? Well, starting with y is the vector of all y's. So y1, y2, all the way till we get to yn. Okay, x, sometimes this is called the design matrix, right? And first we have ones, and these ones are for this intercept term, okay? And then we have our x1, x2, etc. to xn, okay? So for the simple linear regression, that's all you have is the column of ones and the column of x's, right? And later when we go into multiple linear regression, we'll have a more complicated design matrix, okay? Next we have beta, which is our model parameters. So beta 0, beta 1, right? And again, when we have multiple linear regression and we have a more complicated design matrix, then our beta terms are going to be, there's going to be more of them as well, okay? And lastly, let me erase these lines here. So lastly, we have epsilon, which is all of our model error terms. So epsilon 1, epsilon 2, all the way to epsilon n. Okay, so let's talk about the size of each of these vectors and matrices. So this first vector is n by 1, right? So our sample size by 1. Okay, the design matrix is n by 2, right? And whatever we have, so we have 2 columns, so since x is being multiplied by beta, this needs to match, so this is going to be 2 by 1, right? So when you multiply x times beta, basically like the 2's cancel and you're left with an n by 1, okay? And then this is also an n by 1. All right, so there you have it. This is our simple linear regression model using matrices. Now, how do our model assumptions look different? Well, when we have our model written like this way that we originally talked about it, we had the model assumption that our error terms, epsilon sub I, equals 0. The variance of these error terms equals sigma squared, right? So it's homogeneous variance, so there's no I, right? There's no subscript I. It's always exactly the same variance for all I. And then also we have the independence, so the covariance between one error term and another error term, okay, equals 0. So as long as I doesn't equal j. So 2 different error terms, right? And so this is the way we wrote our model assumptions previously. Well, we can write them a little differently now that we have matrix notation. So how are we going to write them? Well, starting with the expected value of epsilon. So instead of epsilon sub I, now it's this vector of epsilons. This is going to be zeros, right? And it's not just a single 0, but if this is n by 1, then this is a vector of zeros, an n by 1 vector of zeros. Okay. All right, and then our variance of this vector epsilon, right? If we take the variance of this, what we have is a matrix, okay? When you have a vector, the variance of a vector, so this is an n by 1 vector, what you're going to be left with is a matrix that is n by n, right? And what we have on the diagonals are the variance. So this would be the variance of the first epsilon, the variance of the second epsilon, all the way down to the variance of the nth epsilon. And then on the off diagonals, you have the covariances. So the covariance between the first and second, between the second and first, which is the same. And then, so they're all zeros on the off diagonals. Okay. And of course, we can write this much neater. So the way we write this variance, let me go ahead and write it here. We write it as sigma squared times I. Okay. Where I is our index matrix, right? And maybe you remember from your linear algebra class, I equals, it's just a bunch of ones in the diagonals and then zeros everywhere else, okay? So we can see that when we multiply sigma times I, what we'll get is what we see here, all right? Also, we can use these model assumptions to find things like the expected value and variance of y. Let's go ahead and do that really quick before we finish up this video. So starting with the expected value of y, right? Now this is a vector. So the expected value of that vector y, okay, equals the expected value of x times beta plus epsilon, right? And we can put this expected value in to each piece of the sum, plus the expected value of epsilon. And we've already talked about the expected value of epsilon. We're assuming that's to 0. And this guy is a constant, right? Remember, we're assuming x is non-random. Beta is the model parameter, so those are also non-random. So this is just x beta and then plus 0, right? So the expected value of y equals x beta, okay? And then also the variance of y is the variance of x times beta plus epsilon, which x times beta is, once again, it's not random. So when you take the variance of it, you get, so you have the variance of x beta plus the variance of epsilon. This is 0 since it's not random. And you're left with the variance of epsilon, which we've discussed is sigma squared times I. So this is the variance of y. Okay, and the reason why we have this vector notation is it's going to make things a lot easier, especially when we have more complicated design matrix. All right, so when we go into the multiple linear regression case. Okay, so in the next few videos, I'm going to be using this matrix notation to kind of walk through some of the derivation that we've already discussed, but you'll see that this matrix, using this matrix notation, we actually will arrive at our answers in a much more efficient manner.